Welcome, everybody. It's my pleasure today to introduce Matt Piekenbrock, who will tell us about spectral relaxations of persistent rank invariants.
Okay, thanks, Henry. Yeah. Yep, as he said, I'll be talking about spectral relaxations of the persistent rank function. This is joint work by myself and Jose Perea at the Corey College of Computer Sciences, Northeastern Boston. Jose is also in the Department of Mathematics, of course, but I am a computer scientist. Okay, so let's continue. Yeah. Oh, there we go. Okay, so in the year 2024, we have many mappings from persistence diagrams to function spaces. Um, let's see. So we have the persistence landscapes by Bubenik, they're very well known. And we also have their associated learning applications. We have the persistence images by Henry and many others, which places sort of a Gaussian or a kernel function at every point in the diagram and produces a persistent surface from which you can extract features, again, for the purpose of machine learning applications. And you know, we have many such learning applications nowadays, actually. And in fact, we have many maps nowadays, from persistence diagrams to some features to some vectors that are used for a variety of applications. Bubenik has a sort of great overview of many of them. So I would say that many of these mappings have some commonalities to them. So of course, many of them vectorize persistence information. Many of them are sort of functions or construct functions from persistence diagrams or persistence information to optimize certain maybe like topological losses. Inherently, all of them use the notion, the defining feature of persistence, the stability of persistence diagrams. And what we would like to do with many of these featurizations is connect to other areas of applied mathematics. So when I started this project, I asked, can we achieve these goals without computing persistence diagrams? So that's what I'm going to talk about in this talk. I'm going to introduce a spectral relaxation of the persistent rank invariants, which is a sort of smooth interpolation between the persistent rank function and certain types of Laplacian norms. The benefit of this type of relaxation is that it can be 1 plus or minus epsilon approximated in effectively quadratic time. The computation itself can be done in a completely matrix-free setting. So in linear memory, linear in the size of the complex. And just like persistence images or any of the other featurizations, we have a variety of applications to pursue related to optimization, metric learning. Excuse me 1 second. Sorry. Okay. So, okay. So I thought I might front load this talk with just introducing the relaxation and talking about the rank invariant. So as many of us know, there's a sort of natural duality between persistence diagrams and this notion of the rank invariant. Typically, the persistence diagram is introduced as the set of pairs, I and J, in the upper left half plane that satisfy this criterion that the multiplicity function at that point is non-zero. Where this multiplicity function right here is sort of defined as via an inclusion-exclusion formula of persistent Betti numbers. And one of the nice things about these Betti numbers is that they're characterized themselves by the multiplicity function. And so when I mention the duality between persistence diagrams and the rank function, this is sort of what I'm talking about. And this is sort of summarized by the fundamental lemma of persistent homology. The diagrams characterize their ranks. In recent work, this has really been extended in a variety of ways. Chazelle has studied this in the measure theoretic setting with persistence measures by replacing the coefficient with the reals. The stability of these invariants has been studied in the multi-dimensional persistence setting or multi-parameter setting. And even more recently, these have been really generalized and studied very rigorously through the lens of Mobius inversion and zigzag persistence and the like. So I'm going to stick with the tagline by Chazelle when I think about the rank invariant. That is, I'm going to focus on the reals, and I'm going to say whenever a persistence diagram is sought, it is enough to construct the corresponding persistence measure. In other words, if I have a persistence diagram shown on the left here, this induces a integer valued function on the upper left half plane here. And what we know from the theory of persistence measures is that if you can actually construct this function, that is enough to fully characterize the persistence diagram on the left. I hope that's clear. Yeah. So this was our starting point. So now I can sort of rephrase the goal of this relaxation. What do I mean when I say spectral characterization of the rank invariant? What I really mean is I want to take this integer valued function on the left-hand side here, and I want to relax it smoothly to obtain a smooth function that we can use for learning applications. Yeah. And the way that I'm going to do that is I'm going to look at the rank of this map here, and I'm going to try to come up with a spectral relaxation that is phrased in terms of sort of singular values. Okay, so that's the intro of this talk. I'm going to front load this with the theory, and then we'll go into applications very quickly. So the rank, how we started this relaxation was we started by revisiting the rank computation itself, the rank of this map here from the homology at simplicial complex at index I to the homology at of the same filtration at index J. So as we all know, this can be rephrased as the dimension of a certain quotient group. And this quotient, this second term of the quotient is actually an intersection term because it has to be a subgroup of the numerator, if you will. So this is really the function that we're trying to relax here. If you distribute the dimension function, you get two separate terms. The blue term, the left term, is very easy to handle with rank nullity. This gives us a direct way of getting a simple matrix, which we can compute the spectral decomposition of and relax. It's really the right-hand term, the persistence part between I and J, that we want, that poses some difficulties in terms of relaxing in its traditional form. So I've given some algorithms here, both general linear algebraic algorithms and persistence-specific algorithms that can all compute this right-hand term. They're all cubic time and quadratic space and sort of difficult to relax, I would say. So the key technical observation of our relaxation can be summarized as follows. If you have a filtered boundary matrix shown here, and you take so there's this sort of nice property of persistence that if you take any lower left submatrix of the filtered boundary matrix and you look at its rank, it will match the rank of the reduced matrix, the sort of pivot matrix after the reduction. So this is due to the so-called pairing uniqueness lemma. And so it can be used to, that is said again, the pairing uniqueness lemma can be used to show that if you take the rank of any lower left matrix of the filtered boundary matrix, it will match the rank of the corresponding lower left matrix in the reduced form. And sure enough, it turns out this can actually be used to derive an expression for the persistent Betti number that is just a summation of ranks of boundary matrices. And this expression of persistent Betti numbers can actually be used to deduce diagrams, it turns out. So let me just show you two expressions. Here's the persistent Betti number, and here's the multiplicity function. These are somewhat well known. For example, one is used to show the correctness of the reduction, but recently it's sort of been realized that it's actually far more general, this sort of pairing uniqueness lemma, because as pointed out by Bauer and many others, any algorithm that preserves the ranks of these submatrices is a valid barcode algorithm. So this is sort of the key technical observation of our relaxation. So let's move on to the relaxation itself. So we started by looking at the rank function because we're focused on the reals. We have this nice equality here between the rank of a given matrix, let's say a boundary matrix, and the composition with its adjoint. And what we can do is to describe this rank function is we can summarize it as a sum of eigenvalues composed with the positive sign function. So this will be a positive semi-definite matrix. Its eigenvalues will be strictly non-negative. And so what we can do is we can apply the sign function that maps everything that's positive to 1, everything that's 0 to 0, and we recover the rank function, right? So our goal, or our strategy, is to take sort of this sign function and relax it with this function phi, which is parameterized by this hyperparameter tau, this sort of regularization parameter, if you will. And our particular choice of phi will be a smooth Dirac measure. So this particular choice of phi, one can show, induces a unique spectral function on the positive semi-definite cone for every tau. In other words, if you give me a matrix X, I can produce a new operator, phi sub tau, given by computing its eigen decomposition and applying this regularized sign function to its spectrum. And this gives me a bona fide new operator that is differentiable on the positive semi-definite cone, so long as tau is greater than 0. And one of the benefits of this type of operator is that its trace, the trace of this operator, is exactly sort of the summation of this relaxed sign function itself. Okay, so that's I won't go into the properties. You can find them in the paper, but that's sort of the overall relaxation. So to sort of make this relaxation a bit more concrete, I thought I might give an example. So in many applications in scientific computing, you start off with a linear system, AX equals B, you want to solve. And you typically, if there's no solution, you relax it first to a least squares formulation. And then to penalize the solution vector, you might add a sort of a norm on the solution, and then you might regularize with some parameter tau. The minimizer of this particular optimization is given by the regularized pseudo inverse. And just as a pictorial example of what this is doing, if you can imagine fitting a least squares fit through a set of points, what this regularization is doing right here is it's sort of preventing the function produced from overfitting to the set of data points you're trying to fit to. And so this is very commonplace, right? In machine learning data science applications, this is very common. What we have is, or what we can show is that if you take this phi function for a particular choice of parameters, and you set it equal to sort of this particular function right here, the corresponding operator that you get is precisely this sort of regularized pseudo inverse, the nuclear norm of which is precisely this sort of phi expression applied to the singular values. And so this has a name. It's very popular. It's called the Tikhonov regularization. It's often used in L1 regression settings. And so because of our formulation here, in some sense, if we just apply this straight up to the singular values of our previous rank invariants we derived, in some sense, we can just get for free a Tikhonov regularized Betti number, if you will. And so this was actually what was used to produce this plot right here. So here I took my persistent Betti, my persistent rank function shown on the left, and I did a Tikhonov relaxation of it, and that produced sort of the smooth function on the upper left half plane. Okay. So why might you want to do this? Well, here's an optimization application that you might want to do. Imagine you have a parameterized filtration of interest. In this case, it's a noisy circle filtered by a codensity estimate. And this codensity estimate itself is parameterized by a bandwidth parameter that controls the quality of the density estimate. And for some values of this bandwidth parameter, the circle is very apparent in its corresponding Ricks persistence diagram, let's say. And for other parameters, not so much. It basically becomes homeomorphic to a disk. So what you might say is, let's say I want to find whether or not a given filtration has topological structure in the sense that it exhibits some non-trivial persistence. You could phrase that as a type of optimization shown here, where you want to maximize the persistence of, let's say, the highest H1 class, let's say. If you look at the vineyard of this particular example by varying this bandwidth across all valid parameter settings, what you get is a function that looks like this. So what I've done is I've fixed some parameter values here. I fixed a box in the upper left half plane, and I've enumerated this vineyard. And whenever this vineyard intersects this box, we get a multiplicity of 1 through the multiplicity function, and everywhere else it's 0. And so you can imagine if this was your objective surface that you want to optimize in the optimization setting, this is very hard to optimize. It's an integer valued function. The gradient is 0 everywhere, right? So if you come from the compressed sensing world, your first guess to relax this type of optimization problem is to use the nuclear norm. So if we just take our multiplicity function here and we replace it with the nuclear norm, this is sort of the tightest convex envelope of the rank function in the unit ball of matrices. What we get is the following red function here. This is a smooth function that you can optimize with first order methods, but as you can see, its minima doesn't line up at all with the objective surface that we want it to sort of mimic, if you will. But so instead, we try our chosen form of relaxation, our Tikhonov relaxation, and it also does not perform very well. You can see it's sort of a tighter relaxation in the sense it becomes closer to the sine function, but the minima don't correspond again at all to the function that we want. So even though we could optimize it with a first order method very easily with, say, gradient descent, it wouldn't lead us to anywhere useful. But we have a guarantee, right? So we know that this regularization parameter, it's sort of an interpolation. And as it shrinks down to 0, we should get arbitrarily close to the rank function. So if we just shrink it just a little bit, sure enough, we get a function that, again, we can optimize as with any first order method. But its behavior sort of matches the type of behavior that we want to see. And you can continue sort of doing this, sort of increasing the regularization or sort of decreasing the regularization parameter closer and closer to the sine function to get a closer and closer approximation to the rank function at the cost of smoothness. And so this actually motivates many algorithms as an optimization. What you can do to sort of optimize these types of surfaces is you can set the regularization parameter, optimize it, and then decrease it, and then optimize it, and sort of alternate in this form. And this has a name. It's called the soft thresholding or the iterative thresholding algorithm. And so this is, again, very popular in the world of compressed sensing and optimization in general. And the benefit of this spectral relaxation that we're proposing here is to sort of bring some of these algorithms to bear in the world of persistence. Yeah. Okay, so let me slow down a little bit, but yeah, so that's the idea. Okay. Okay, so I want to talk about computation because it's very important, computation. As we all know, persistence is can be a very difficult thing to compute. It's often said to be cubic time in the size of the filtration, but the filtration itself may be very, very large. For example, in H1, the size of the filtration is actually cubic, and so or could be cubic if you let the parameter sort of go out to infinity. And so the persistence computation has a corresponding complexity of something like n to the ninth, where n is the number of data points you start with. And so this is sort of unscalable for these big machine learning applications. So one of the things that we wanted to focus on was trying to sort of decrease that, trying to obtain sort of these persistence invariants that are differentiable, but at a lower complexity than that of the persistence algorithm. Of course, there's a very simple way of obtaining these spectral relaxations. You can take any matrix, which for us will just be a boundary matrix or a type of Laplacian, and you can take its eigen decomposition. We know how to do that in effectively cubic time in quadratic space. I'm going to ignore the Strassen family for now. But there's actually a way to do this in quadratic time and linear space, which I didn't know about. You can obtain the eigenvalues of any positive semi-definite matrix, it turns out, in quadratic time, if your matrix vector action can be done in linear time. The idea is very simple. You start off with a random vector in Rn, and then you just apply your matrix repeatedly to this vector. This creates a matrix called K. You could, for example, take this matrix K and do a QR decomposition. One can show that the vectors you will get will be linearly independent. This gives you a set of orthogonal factors that you can use to rotate your matrix to a structured type of matrix in tridiagonal form, shown here. You might say, well, Matt, the QR decomposition takes cubic time. We definitely can't do this, right? This will also take quadratic space. But it turns out every symmetric matrix that can be expanded this way admits this so-called three-term recurrence. In other words, to obtain this final decomposition here, which contains our eigenvalues, it is enough to have at most three vectors linear in size in memory at any given time. So I won't go too much into details, but the idea, the takeaway is that you can actually obtain eigenvalues, all of the eigenvalues of a matrix, using a linear amount of memory, if your matrix vector action is fast enough, essentially. And this has a name. It's the well-known Lanczos method for Krylov expansion. And so this is an image, an animation I actually made, which does exactly this. It starts off with just a matrix, which is given in a matrix-free setting. We treat it as a black box. It performs matrix vector multiplications, and we obtain Rayleigh-Ritz values, which are approximations to the eigenvalues. And it turns out that in 1984, well, here's a theorem shown from 1984 that justifies that you can indeed do this in quadratic time and in linear space if your operator allows. And when executed in exact arithmetic, I might add. Yeah. So we can actually do better than this. More recently, it's been shown that you can approximate these. Let me take a step back. So what we want to do ultimately is compute sort of quantities of this kind, which are traces of matrix functions. So here's a matrix function where we apply phi to it and we get a new operator. And ultimately what we want to do is we kind of want to compute the trace of these quantities. Yeah. Recently, it's been shown that you can produce unbiased estimators of these types of operators by first performing a Lanczos expansion and then averaging quadratic forms. And this has been called the stochastic Lanczos quadrature method. And with Laplacian matrices, which are the types of matrices we'll be dealing with here, the matrix vector action is in fact linear in the number of p+1 simplices. So one can show, we have in our paper, that sure enough, this leads to an epsilon approximation with some success probability that again takes linear amount of space to obtain. So the tagline is, if you completely missed all of that, is that matrix vector multiplications is all you need. So to obtain these persistent rank invariants, all you need is the repeated action of a matrix multiplied by a vector. So no reduction, no pivoting, no need to store the chains that correspond to the co-boundaries. None of that is needed. Just a fixed boundary matrix, perhaps in the GPU, maybe permuted in an optimal way to for cache purposes, and then repeated action with that matrix is all you need to estimate these quantities. Okay. So here's a plot by a recent package called the IMate package. And this just kind of shows the scalability of this type of computation, even upwards of 10 million dimensions in the size of the matrix. You can compute or approximate these quantities in less than 10 seconds. So this really, shows, in my opinion, sort of true scalability at the level of the scalability that machine learning methods actually need to compute these quantities. Yeah. And so I ran an experiment. This is a sort of preliminary experiment where I took a torus and I started with a very densely packed torus with uniformly randomly spaced points, and I did landmarking on this torus to sort of get a set number of points, essentially. And what I did is I computed the persistent homology, the H1 persistent homology, with the RIPS filtration on this point set. And I use RIPSer, which computes persistence in Z2. It's perhaps the most well-known persistence software out there currently. And RIPSer performs very well. It's very, very fast, as many of us know, until you sort of reach a certain threshold, which for me was about 2,500 points, where all of a sudden my computer completely slowed down and I couldn't actually handle the size of the filtration. I couldn't compute the homology of the point cloud that I wanted because RIPSer was just taking up too much memory. Now, RIPSer, compared to other persistence software, is actually very memory efficient. It's enormously memory efficient. It does many, many tricks to remove large parts of the computation, and it itself does have a sort of implicit matrix reduction to it. But RIPSer is a reduction algorithm, and all of the reduction algorithms asymptotically have to have quadratic space. They have to, as part of the reduction algorithm. So even though a large constant factor is reduced, asymptotically, again, RIPSer will use a quadratic amount of space. And so that's sort of what I'm trying to show here, again, on a log scale, even at 2,500 points, Ripser is using upwards of 10 gigabytes of memory. And if I actually just increase this to 3,500, it gets up to 100 gigabytes of memory, which very quickly becomes just not scalable, even on a cloud setting, for example. On the flip side, what I've shown is the Laplacian-based matrix vector action approach that I've sort of detailed here. I've shown the memory usage of that with the red line, and we can only compute these invariants with coefficients in R, keep in mind, so we're not doing Z2. But as you can see, even upwards of 2,500 points, we can compute these invariants using less memory than a Chrome tab nowadays. So this really sort of enables the potential to compute persistence invariants for data sets that are so enormous that you simply have no other means of actually getting at these invariants. Now, I've talked a lot about the persistent rank function and these rank invariants. The persistent Betti number, which sort of counts the number of points in the upper left, in some sort of box in the upper left half plane. But it turns out you can actually compute diagrams this way as well. I mean, I mentioned this at the beginning, but I didn't actually tell you how to do it. The reason is that the algorithm is actually not mine, but that of Chen and Kerber. It's a brilliant algorithm, sort of lesser known, from 2011. The title of the paper was an output-sensitive algorithm for persistent homology. And what they actually showed was you can devise a divide and conquer based approach. The divide and conquer is sort of on the upper left half plane itself in the index persistence plane that computes these persistent pairs via sole rank computations. So in other words, if you can compute a Betti number, that's actually, again, sufficient for computing the full persistence diagrams, all of the pairs. And so what we actually can just transport our results on the rank computation, for example, this iterative rank computation, directly to this setting. Okay, so that was a little faster than what I practiced, but I'll leave some room for questions. I do want to mention some acknowledgements. The persistent Betti number expression I gave is somewhat it's somewhat not well known. I would say it's a little unorthodox or non-traditional. The only derivation I've actually seen of that particular expression, the unfactored expression, is due to the computational topology book by Yusu Wang and Tom Day. I'm told that you can work it out using the prior works, but the only explicit expression and proof I've actually seen is actually due to this book in 2022. I just want to give acknowledgments to Chen and Kerber. The rank-based persistence algorithm is very interesting. It's very neat. It's never been implemented to the strength of, let's say, Ripser, the industrial strength, but here I have implemented it, and although the timing is sort of not nearly that of Ripser in terms of speed, the memory is there. So it is a low memory alternative for the persistence computation. Yeah. Yeah, I also just wanted to thank Bauer and Nemli for, these papers were very, very useful for me in sort of developing this. And the 1 plus or minus epsilon trace estimation procedure is due to Ubaru and Mushko specifically. So this paper in particular established that the Lanczos method is actually stable and finite precision. So I didn't want to cover it here because I thought it would take too much time. I gave this theory here, which is only true for exact arithmetic, which was known in 1984. It wasn't actually known until very recently that this is essentially true, with some asterisks, in finite precision as well, in the sense that the Lanczos method, the base Lanczos method, is actually sort of optimal in its stability in finite precision. Yeah. Right. Okay. And you can actually try these trace estimators yourself. I have a GitHub here, which I can click, and it leads to this package documentation. You can install it with PyPy. You can review the theory. I have some guides here. So all of this can actually be tried just with a simple Python install. If you have any issues, don't hesitate to let me know. Yeah, thank you for listening.
All right, before we get to questions, let's briefly unmute ourselves and applaud for Matt. Great. Questions for the speaker? I'll start with one. Matt, could you go to one of your pictures of the the smoothings of these rank invariants or the diagram? So you have the like blue and yellow diagram, and then you have the I might call it the slightly pixelated
Yeah.
approximation.
Here we go. Yes, right here.
Yeah. So the one on the left is, it's a piecewise integer function,
Mhm.
right? Um, and then so the one on the right,
Mhm.
what are the properties of this function? Is it on the function on the upper, left diagonal to the reals? Is it continuous?
Yeah, so I
Etc.
skipped the properties again for time, but so when I talk about this function, I'm really sort of thinking about just an individual point for now. So
Yeah.
at individual point, this will be integer valued, and this is a rank computation. So you compute the rank of some boundary matrices, you just get an integer at any of these specified points. With our spectral relaxation, um, instead, you compute a norm of a particular type of Laplacian. And
Mhm.
in terms of differential, yeah, so there are monotonicity properties about this function. Uh,
Yeah.
there are differentiable properties about this function. In particular, the positive semi-definite matrix that you start with, the Laplacian matrix, the trace of that um, as a function is differentiable on the positive semi-definite cone. Um, and it's a particular type of matrix function called an operator monotone function that has some other properties, but the properties are sort of not, I can't visually show what, I guess their connotations. Yeah. Yeah.
Sure. And
Mhm.
are any of those properties preserved by the one on the right? Like monotonicity, for example, or
Oh,
not
yeah. Yeah.
not so.
So the monotonicity property um, is actually with respect to like the partial order on the positive semi-definite cone. Um, yeah, and it is obeyed by this relaxation on the right. Yeah, that's how I computed it.
Nice. Okay.
Mhm. But this is not the only choice of that. So you can choose a particular. There are many choices of this type of sign relaxation that you can choose. I have one that's based off of the heat kernel, for example, that I didn't show. That you can also use. Basically, anything that fits within this formulation of this Dirac measure. Yeah, anything like here, anything that can be expressed as a summation or an integral um, of eigenvalues. Um, uh, yeah, where the phi function itself is expressible as an integral of smooth Dirac measures. Yeah. So we give a few examples in the paper. Yeah, but. Mhm.
Further questions? Yes, Junyan.
Hi Matt. Thank you for the talk. The memory usage plot is very impressive. Um, so I guess my question is, so you are basically doing two approximations. The first is approximating the rank with a smooth function, and the
Mhm.
other being the estimation of the trace function.
Right.
Um, and when I choose the approximation of the rank function, like if I choose a like like more accurate approximation, like I do not lose anything in terms of like memory or like computation time, right?
So It's a great question. Yeah. So you don't lose anything in terms of memory, but you definitely do lose computation. So the way that the trace-based approximation works is it iteratively does matrix vector multiplications. It does a finite degree Krylov expansion, and then it basically does an aggregate statistic on the eigenvalue estimates of that Krylov expansion. And that can be a fixed degree Krylov expansion. So you can do a 20-degree Krylov expansion, for example. The issue is that if you're estimating something that's very easy to estimate, that's very smooth, and that depends on the magnitudes of the eigenvalues, like the Frobenius norm, for example, or the nuclear norm, then you can estimate these quantities very quickly. But as you get closer and closer to the actual rank function, which sort of discards the magnitudes of the eigenvalues, right? It treats them all as either positive or zero, essentially. It becomes harder and harder to approximate with a Krylov expansion. So you can still get it at linear memory. It's just the number of matrix vector multiplications that you would need to do could be exponential. That being said, this is a very relatively new area. So there's a lot of recent work on this. For example, I gave a rate, which is actually a very conservative rate here. This epsilon squared right here suggests that this is a crude Monte Carlo method that's, you have to do 100 times the work to get a 10 times reduction, basically, in precision. Or yeah, but it's actually been shown that there should exist a way of getting this down to just an epsilon approximation. We just don't have an algorithm yet for that. Yeah, and there are other variance reduction methods that you can use to sort of reduce the variance of the estimate and thus decrease the computation time. But it gets very hairy very quickly. We have not been able to produce, at least for very large examples, an estimator that is truly competitive with the persistence algorithms on outputs that the reduction implementations can handle. Yeah. So
I see.
That being said, there are many data sets that are just so large that the implementations they just don't have enough memory for them. So we kind of see this as a way of, in those settings, if you want to measure the homology of the observable universe, for example, if you just let a supercomputer go, just doing matrix vector multiplications, perhaps accelerated on the GPU, check back in a week, you should be able to eventually get an accurate estimate of the Betti number, the persistence diagrams, basically any of the persistence, invariants.
I see. Thanks.
Further questions? Yes,
Yeah.
Dave?
Yeah. Matt, I enjoyed the talk very much. So you showed us the example of the torus with large number of sample points. And then you just mentioned the Betti number of the universe. Is there something in the middle that you've tried which has been somewhat intractable by standard methods where you've been able to get results in applications?
So we've mostly just focused on synthetic just to get the implementation going. For example, the torus. We do have plenty of applications in mind, like actual real world data sets. The issue is we don't yet have an in-between in terms of time and space. So basically you can use a reduction implementation, which uses quadratic amount of space and is very fast, let's say RIPSR, or you could use our approach, which is an iterative approach, which is very low memory, but requires many, many, many matrix vector multiplications. In other words, it's very slow time-wise. What we would like, ideally, is sort of an in-between where you sort of accelerate, you decrease the amount of computation time up to the amount of memory that you can allocate, and then go from there. But we don't quite know how to exactly do that, at least for rank computations. Yeah. So I guess the answer to your question is no.
Yeah. But thank you. I appreciate it.
Yeah. But that being said, with the torus, this is a real benchmark. So it looks maybe overly smooth. It looks very, it looks like I just plugged in an analytic function here for the red, but I didn't. That's actually true. High watermark memory usage as measured by a software called Memory. The reason it looks so smooth is because this is a log plot. So the constant factors eventually just completely die down. And it really is asymptotic behavior that we're quantifying here in terms of space. Yeah.
Good. Good. Thank you.
Yeah.
More questions? Let me ask one more. So Matt, if you go back to those plots we were discussing earlier, like the persistence diagram type plots.
The beginning, yeah.
Yeah. So the question is, I mean, the diagrams on the left, for understandable reasons, they look like sort of unions of corners of rectangles, right?
Right.
The one on the right almost looks like almost unions of half spaces. I mean, is there a reason one might expect this?
So it's a little unclear to me exactly what these types of interpretations we can get, or the interpretations that we can get from this type of plot. One of the issues is that I guess I'll give you a partial answer. So persistence is very scale variant, right? So in the same way, the rank function is also scale invariant. That's kind of what we see here. So it doesn't depend on the magnitude really of the eigenvalues. Whereas based on the relaxation that you choose, if you want smoothness, you have to depend, more on the magnitudes of eigenvalues. And that sort of means that you're going, the corresponding function that you get in this upper left half plane is going to depend more and more and more on the actual magnitudes of the eigenvalues involved in the decomposition, which could explain why, as you go further right, you include more simplices, the eigenvalues increase in magnitude, things like that. But overall, I guess I don't have a great interpretation of going all the way from eigen decomposition to upper left half plane. It's a little hard. Yeah. I'm open to a collaboration to figure it out, though. Yes. Yeah.
Thanks. Very interesting. Any final questions?
So I have another question, if there are no other questions.
Sure.
So you mentioned the slowness is due to the fact that it's a Monte Carlo estimation. Are there like MCMC methods to like estimate the rank?
So the difficulty, I shouldn't say slow. So it really depends on what you're computing. So it's a multifaceted issue. One issue, let me just go to this slide. Okay. So no, sorry. This slide. So one issue is that the rank function is very hard to approximate. So if the function that you're approximating is, let's say, the nuclear norm, then it is very fast to approximate. Just a few matrix vector multiplications and you're done. So even though the Monte Carlo rate is, the convergence is 1 over epsilon squared, in practice, if you have something that depends very much so on the magnitude of these singular values, especially if your matrix is well conditioned, it's within a constant number of matrix vector multiplications, you can get a very high precision estimate. Actually, it's as soon as you keep increasing this, as soon as you get closer and closer to this rank function, do you sort of lose conditioning in the matrix, and things sort of become harder and harder to approximate. And so it depends on the application. So if you want to actually obtain the integer valued rank function, or you want to actually use this method to obtain the persistence diagram, you can do so, but you're going to pay for that cost in terms of time. On the other hand, if you just want to obtain a gradient, let's say let's say the orange, for example, or even the green relaxation, for learning purposes. If the objective surface is approximated fairly well by this not so heavily regularized spectral invariant, then you can obtain them very, very quickly. Yeah. So, and all of this, I actually have all of this with, I was going to show it, but with PyTorch, you can just implement an auto differentiable computation graph, plug in the spectral relaxation and its derivative, and because the boundary matrices are just sparse tensors, you can just get gradients for very, very quickly that you can use for optimization of whatever it is you're trying to optimize. Yeah.
So you're saying that the persistence Betti numbers in and of themselves are difficult things to compute, and so like you cannot go around that.
So yeah, which in some sense, recovers what we already know about them. They are very hard. Actual true numerical rank computation is hard. That's just true. But this method kind of gives a way of just approaching that in a smooth sort of interpolation way. You can approach the hardness of that computation and get arbitrarily close to it if you so choose, or you can relax it and you can just see if that's good enough for your application. Let's say you're trying to make a featurization that depends on the upper left half plane, for example. You could, it's not too hard to imagine that perhaps for some large regularization, it's actually enough. Just as we take persistence images and we get these features derived from these diagrams, you can imagine, well, maybe we just do a couple of matrix vector multiplications, extract very loose approximations of these persistent invariants, and that may very well be enough for classification purposes, learning purposes, etc. Yeah.
I see. Thanks.
All right. Well, how about we end the recorded portion there? Thanks so much, Matt.
Yes.
And thanks to all the audience.